today's video, we're going to look at simplifying radical expressions. Now, this is a skill we need to improve on and make sure that we're really solid on for our future sections when we start adding and subtracting radical expressions. There are two techniques for simplifying radical expressions. We can use the prime factorization, where we break up each term into its prime factors, or we can use perfect square and perfect cube factors. This second technique is the one that we're going to highlight today. So if we're using perfect square, perfect cube factors, we need to know what they are. So I've created here a list of perfect square and perfect cube factors. This first table, let me see if the next slide has, well, let's look at this table. This table is more complete. So here's a value of n. In this first column, we have our perfect squares, so n squared. Our perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81. And there are obviously infinitely many more, but this is all I could fit on this slide. On Blackboard, you guys will find a more complete table, but this is just to give you guys an idea. And then in the next column, we actually have our variable perfect squares. So x squared is a perfect square. The square root is x. X to the 4th is a perfect square, x to the 6th is a perfect square, 8th, x to the 10th. One of the things you may notice is that your perfect squares in terms of your variables with exponents, your exponents are all even numbers. For our perfect cubes, we've got 1, 8, 27, 64, 125, 125 being 5 cubed. That's how we would read this table. Again, these are just a handful of perfect cubes, but they're the more common perfect cubes. They're the ones that you're going to try first for the most part. And then we have our variables, x cubed, x to the 6th, x to the 9th, x to the 12th, x to the 15th. And this pattern shows that as long as our exponent is a multiple of 3, then it is a perfect cube. And then I have a few perfect fourths here because we will see that index in some of our radical expressions. 1, 16, 16 is 2 to the 4th, 3 to the 4th is 81, 4 to the 4th is 256. Again, I stop it here because these values grow very, very quickly and we probably won't see too many perfect fourth factors that are larger than 256. For our variables, x to the 4th, x to the 8th, x to the 12th, again, if you notice a pattern there, the pattern is that our exponents are multiples of 4. So for our variables, perfect squares, the exponents are multiples of 2. For our perfect cubes, the exponents are multiples of 3. For our fourths, the exponents are multiples of 4. I encourage you guys to get onto Blackboard and maybe print the table that's available for you guys or make your own table. It's a really nice guide when you guys are first learning how to simplify radical expressions, something quick to see what you should be trying versus not. It might help you recognize a little bit more of these perfect squares and think about them in certain problems that you need them. So simplifying the radical expression. What we want to do is take our radicand, which is 18, and we want to factor it. But we want to factor it in a very special way. What we're trying to find is the largest perfect square that is a factor of 18. Remember that a factor is something that will divide evenly into 18. With this, if you look back at that other page, looking at our slide for perfect squares, what's the largest number here that will divide evenly into 18? Well, 25 obviously won't because it's larger than 18, 16 won't, but 9 will. Now notice I'm starting from the bottom of this where my numbers are larger and moving to the smaller numbers. That way I ensure that I get the largest perfect square. So the factors of 18 are 9 times 2. And since 9 is a perfect square, I like to circle it, and that is my reminder that I'm going to factor it out of the radical. When you factor it out of the radical, you actually have to take the square root. What is the square root of 9? It is 3. Since 2 is not a perfect square, it remains under the radical. This simplifies to 3 square root of 2. The cube root of 40. Now we're looking for the largest perfect cube that is a factor of 40. So going back, here are our perfect cubes in this middle column. 64 obviously won't work because it's larger than 40. 27 is not a factor of 40, but 8 is a factor of 40. So we're going to factor this to 8 times 5. And some of this requires trial and error. You'll use your calculator to make sure that they divide evenly. 8 is a perfect cube. Now, when we factor out the 8, we need to take the cube root. Pay a lot of attention to your index. Your index is really important when simplifying. The cube root of 8 is 2. And since the 5 is not a perfect cube, it remains under the radical. Notice I made sure that I rewrote that index because that is an essential part to this expression. The square root of 81y to the 5th. In this example, since we're dealing with a coefficient and a variable expression, we're actually going to factor them separately. So looking at 81, and this is a square root, I already know 81 is a perfect square. So I'm just going to circle it so that in my step, when I simplify, I know to factor it out using the square root. Y to the 5th, we're going to factor to y to the 4th times y to the first power. Now, I didn't go back to that slide, but you guys should have it or have a copy of the table from Blackboard. And you know that y to the 4th is a perfect square. Now, when you're factoring, remember, factors multiply to give you y to the 5th. When we're multiplying these terms, our exponents we're actually adding. So our exponent of 5, we're going to try to break it down to two numbers that add up to 5. We want one of them to be the largest perfect square or largest multiple of 2. So y to the 4th is our perfect square here. And now when we simplify, the square root of 81 is 9. The square root of y to the 4th is y squared. And then we have left y to the power of 1 underneath the square root. The cube root of 24, a to the 9th, b to the 4th. Going step by step, looking at 24, the largest perfect cube that's a factor of 24 is 8, and it's 8 times 3. When I look at a to the 9th, because my exponent is a multiple of 3, a to the 9th is a perfect cube. And b to the 4th, we're going to factor to b to some power times b to another power. Remember that these two exponents that we put down here are actually going to be, you can see now where I'm talking about, those two. Those are going to add up to 4, but we want one of them to be a multiple of 3, specifically the largest multiple of 3. So it's going to be 3 and 1, where b cubed is a perfect cube since that exponent is a multiple of 3. Now that we've broken everything down, we simplify. The cube root of 8 is 2. The cube root of a to the 9th is a cubed. We get that by taking 9 and dividing it by 3. And the cube root of b cubed is b. Now we list whatever was left remaining underneath the radical. We have a 3 and a b. The fourth root of 32z to the 7th. Now I'm going to reference back to that table of perfect fourths. That's probably the one column that you know the least well because you haven't seen it too much. But looking at these values in the end of the fourth column, 16 looks like it might work. So let's go back. 32. Will 16 divide evenly into 32? Yes. So we're going to factor this to 16 times 2, where 16 is a perfect fourth. Z to the 7th, we're trying to find two numbers that add up to 7, where one of them is the largest multiple of 4. Well, we're going to have to do 4 and 3. Yes, there are different combinations of numbers that add up to 7, 5 and 2. but neither 5 or 2 are multiples of 4, so we don't want to use that combination. Z to the 4th is our perfect fourth. The 4th root of 16 is 2. The 4th root of z to the 4th is z. And everything else is going to be left under the radical, 2z cubed. Again, do not forget your index in your final answer. If you don't write an index, then it looks like the square root, which is completely incorrect since our problem originally started as a 4th root. The square root of 80y divided by 3 times the square root of 5. Now notice we've got two radicals that are being divided. They have the same index. The quotient rule for radicals says that as long as this is the case, we can take these two and write them underneath one radical. So I'm going to keep that 3 in the denominator out front as a 1/3 times the square root, one giant mega square root of 80y divided by 5. Now the reason we want to do that is because if I can divide 80 by 5, now I'm dealing with smaller values. 80 divided by 5 is 16. So this whole radical is just the square root of 16y. And now we try simplifying. 16 is a perfect square. We already know that, so we'll circle that. And then y, we don't have any factors of y, so we just leave it alone. When we factor the 16 out, we take the square root. So we've got 1/3 times 4 times the square root of y. And we can clean up this expression. 1/3 times 4 is 4/3 times the square root of y. There are other techniques that we can use to simplify that original expression. We'll see it in a couple of days. It's called rationalizing the denominator. But since this problem, the 80 over 5 divided nicely and evenly, we would use this technique as opposed to rationalizing. 5 times the cube root of 162x to the 8th divided by the cube root of 3x squared. That 162, I don't want to try to factor. It seems a little cumbersome. So we're going to use that same technique of combining those two radicals as one. So we have 5 times the cube root of 162x to the 8th divided by 3x squared. 162 divided by 3, you guys can do that on your calculator, is 54. And x to the 8th divided by x squared. If you've reviewed your rules of exponents, when you're dividing like this, we actually subtract our exponents. So this is x to the 6th. Now we start simplifying this radical. The factors of 54, we're looking for the largest perfect cube that's a factor of 54, which is 27, and it's 27 times 2. And x to the 6th, since my exponent is a multiple of 3, this is a perfect cube. So simplifying, the cube root of 27 is 3 times the cube root of x to the 6th is x squared. And what's left underneath the radical is the 2. Now we want to clean this up. 5 times 3 is 15. X squared times the cube root of 2. Just to recap, guys, we have that table of perfect squares, perfect cube, perfect fourths that will help us in factoring our radicands. And we're looking for the largest perfect square, cube, or fourth, depending on the index, that will divide evenly into each of those pieces of our radicand. Make sure you guys are paying attention to index. I can't stress this enough. A lot of times we have values that are both perfect squares and perfect cubes, or perfect cubes and perfect fourths. 81 is one of those values, 64 is another one of those. So you want to be very, very careful and always look back and pay attention to what your index is so that you simplify correctly. Again, this is a skill that we are going to be using when we start trying to combine radical expressions using addition and subtraction. We'll see you guys next time. Thank you.